Hi, biostatisticians. So today I'll be covering 8.3, testing claim about the mean, but I'm going to go ahead and jump right into the question, starting with example 1, which is slide 23 on your notes. So let me read it here. It says the authors obtained times of sleep for randomly selected adult subjects, including the National Health and Nutrition Examination Study, and those times are listed below. And here are the unbounded statistics. And I blocked them out, so we'll have to find them, which basically we're going to enter them into your calculator. 4, 8, 4, 4, 8, 6, 9, 7, 7, 10, 7, 8. I put it in list 1, use stat calculate, and I'll get some things that we need. So, but basically we're doing kind of the same thing we did last week, which is doing hypothesis testing. So we're going to kind of follow those same steps, which first would be step 0, which is get some information, what's given in the problem. Is I see n equals 12. It gives me the data, and I went ahead and calculated the data of the statistics. 6.833. Okay, repeated. Your standard deviation, your SX, would be 1.99240,984. Okay, so these are all the stats that we're going to use, and it doesn't give us necessarily an alpha. So if we're not given an alpha, oh, actually it does. It's alpha equal to 0.05, but I might as well finish the statement. If they didn't give us an alpha, then we'd probably use 0.05 anyways. So with this said, I'm going to move on to step 1. Last week what we talked about is hypothesis with proportions. This week we're going to talk about hypothesis with means. Okay, so with the mean, let's say the null hypothesis, the mean equals to whatever is stated in the problem, which here it says that a common recommendation is the adults should be sleeping between 7 and 9 hours each night. And additionally, we want to know, use the p-value method to test the claim that the mean amount of sleep for adults is less than 7 hours. So that tells you right there. The null is that the mean is 7. The claim is that the mean is less than 7 hours. Okay, so that's what we suspect. And here we should state a statement about what is the mean, where mu is the mean hours of sleep for an adult. Okay, and I didn't mention this in the beginning, but just like in class, you should probably be taking written notes. That'll probably help you learn it a little bit better. So we set up step 1, that's the hypothesis step. In fact, we call this steps 1 through 3. So that is set up. Okay, so we'll keep going. Step 4 is set the alpha. And in fact, I like to group these two. We'll group these at step 4 through 6. Step 4 being set alpha. We already know it's 0.05. Step 5 being to determine the test that we will use. So in this section, we're going to use a t-test for sample means, which is denoted by x bar minus mu times s divided by the square root of n. We will calculate this. Okay. So we got what we need, and we'll go. That's step 5, and then step 6 is to go ahead and calculate the t-test. I'm going to put t-test here. T-test, because in a little bit we want to distinguish that between t-critical. So the difference between each of these sections is there's going to be a different test value, different formula for the test value. That's the main difference from last week to this week. There's a different formula for this t-test. So here I'm just going to substitute 6.833, okay, and then I'll go to a few more. Minus mean is 7 from our null hypothesis, right? I can put that up here too. Over S is 1.99240,984 divided by the square root of n, which is 12 in this case. We'll calculate that. Okay, so for this I get negative 0.28978 or 98 if I round up. Is my t-test. Okay, so the first question says to do it by the p-value method. Again, the method doesn't matter for steps 1 through 6, but if we're going to do the p-value method, step 7 would be to actually find and calculate the p-value. So what's the p-value? The p-value is the probability that I get z-test or t-test and beyond. So this was actually a negative 0.289. So if this is 0 for a t-distribution, then negative 0.289 to negative 0.2898 would be about here. And this would be my p-value. This is what I'm looking for. Okay, I could already tell that's going to be fairly high, but we're going to do it anyways. We're going to find the p-value by doing normal CDF. Normal CDF of that as the lower bound, or I'm sorry, negative infinity. Lower would be negative e to the 99 for negative infinity. Upper for negative 0.2899. Oh, you know what? We've got to correct this. Not normal CDF. We're not talking about z-scores. We're talking about t-scores, so it's actually t-CDF. Okay, so we're going to do t-CDF this time. Second bar is t-CDF. From negative e 99 to upper 0.2, negative 0.2898 with a mean of 7 and a standard deviation of 1.9924. Just make sure here. 1.9924. Okay, yeah, so we're going to do TCDF, lower negative infinity, upper is negative 0.2898. On TCDF, you'll notice it asks you for degrees of freedom. Remember, the degrees of freedom is 1 less than the sample size. So in this case, sample size is 12, degrees of freedom is 11. If you input this, you will get your p-value, which my p-value I find to be 0.3886. So then with the p-value comes our decision, right? So this is still for example 1. Our decision would be our step, part of step 7. And so we would say, since the p-value is greater than alpha, we fail to reject H naught, that the mean number of hours of sleep is 7. So we weren't able to reject the null hypothesis, and so we'll make a statement about the alternative. There is evidence, there is not evidence to suggest the alternative hypothesis is true, that the mean number of sleep is less than 7 hours. The mean number of sleep is less than 7 hours. So this is this is it. That's the p-value method. Now, if we wanted to do the critical value method, which is example 2 on your notes. Yeah, example 2 says, well, actually, they say finding the p-value method without technology. Here's the only thing. Without technology, you would use your chart, your t-chart, go to the row with the degrees of freedom 11, and you would go to the closest t value for 0.29, and you look at the body of the table, and you'll get your p-value from that, okay? This is more precise using technology, so I'd probably kind of err on that side. So that's example 2, doing it with the table. Same thing, just this step would be with the table. So example 2, that's pretty much done. Example 3, that's the critical value method. So meaning we don't have to change much, and I'm not going to change much. The only thing is I need t critical. Okay, and that would be starting at step 7. Again, I'm not going to rewrite the rest of the steps. Critical value. The critical value, or t critical, would be calculated by, in other words, what am I looking for? I'm looking for at which point would I be convinced? Well, we said alpha equals 0.05. I want this value, which we're going to call t critical. How do I find that? Inverse t of alpha equal to 0.05 for our area. Yeah. Since it's left area, I can just say equal to 0.05, and also my degrees of freedom would be 11. Okay. Input that into your calculator. We will get the t critical. So that is what I'm doing. Second varse. Inverse t, 0.05, degrees of freedom 11. I get negative 1.79 or negative 1.796. That's 796. That's my t critical. So now we already calculated t test. We're going to see is t test negative 0.2898. Is that in the critical region? Is that in here? Well, negative 1.796, so this would be 0. Negative 0.2898 would be about here. That's t test. Negative 0.2898. In is not in the critical region, so we would make pretty much the same conclusion. I'm going to write it here. Would be, but for a different reason. Since t test is not in the critical region, we fail to reject H naught. Step 8 would be the same. Nothing changes there. No, the only thing that changed was the reasoning. Okay, so that's the critical value method. Okay, so both equivalent methods both get you the answer. This one for the reason that the p-value is greater than alpha, we fail to reject. This one for the reason that t-test is not in the critical region, we fail to reject. Same ideas from before. Okay, so that concludes that example with using the critical value method or the p-value method, and then the critical value method. Okay. There's also on example 4 a continuation of this problem would be to calculate using the confidence intervals. So we're going to do that. Okay. Now here we want a 90% confidence interval. So this is somewhat brought up in class. I want a 90% confidence interval. Or why why does a 90% confidence interval equate to a left-tailed test of alpha of 0.05? Well, if you think about a confidence interval, and if I want alpha to be 0.05, or I want that part to be 0.05, confidence interval, you actually need 2 tails. So in order for one side to be 0.05, you need to make the other side 0.05, therefore making your confidence 90%. So 90% confidence level is equivalent to a left-tailed test of alpha 0.05. Okay, because this gives you a 0.05 to the left here. Okay, so if we calculate this confidence interval, we should get some corresponding results. So if you recall, for this confidence interval, you would use x bar minus your t critical, your t alpha over 2 actually, which is going to be 0.05, times your s over your square root of n is less than mu, less than the same thing, which I know, I'm not sure you can see. Yeah, it should be x bar plus t alpha over 2 times s over the square root of n. Same thing except plus. Okay, now here what you end up with is 6.833 minus t alpha over 2, which is inverse, again, inverse t of 0.05 turns out to be the same thing, negative 1.796. Times s, 1.992 over the square root of 12, less than mu, less than the same thing on this side, except plus 1.796 times 1.992. Okay, and if you can't see this part, I'm sorry. Or here, I can fix that, I guess. There you go, I think you can see that. You should be able to calculate, type that into your calculator, and we should get our confidence interval. Okay, so I type this in, and I get 5.8 less than mu, less than 7.87. 5.80 and 7.87 hours. So according to this, we are 90% confident that the mean number of hours of sleep is between 5.8 and 7.87. Which, ask yourself this question, is that evidence for the null hypothesis or evidence against the null hypothesis? Well, if we're 90% confident that the mean is between 5.8 and 7.87, that would be evidence for the null hypothesis. Since it's contained, since the null hypothesis is contained, so we would say something like, well, first we are 90% confident that the mean number of hours of sleep is between 5.8 and 7.87 hours. 7.87 hours. Which is evidence to suggest, or in other words, we would have to fail to reject the null hypothesis there as well. So all three methods come to the same conclusion. Okay, so that's example 4 with the confidence interval, but example 1 is here. Example 2 was just do the same thing as example 1 with the t-table. Example 3 was do it using the critical value method. Example 4 was do it with the confidence interval method. Okay, so those are all complete. Okay, now you'll notice slide 25 is kind of in there. I won't go over that. We kind of talked about this in class, but basically you're looking to see the output of these t-tests. You can conduct a t-test on the calculator. I can say that. You should have the data or right, if you were doing this problem, you would have the data in. So you can go to second vars, give me a second, actually stat, right arrow to test, and we're doing not a one proportion, we're doing a t-test, which is number 2 on a stat test, a t-test, and we have data. You would have to input mean of 7. Your list is L1, and this is a left-tailed test, so you have to put less than mu sub naught, and then all you do is calculate. And if you push calculate, you should get negative 0.2898 for your t, rounded. You should get a p-value automatically, which I match up with the p-value I got here, 0.3887. And then they'll also give you x bar, 6.833, and they also give you s, your standard deviation, and n. And then just from that output, you should be able to generate a decision, right? Since your p-value was 0.3886, it's greater than alpha, 0.05, so you're going to fail to reject. So just look at slide 25, look at some of those outputs. You should kind of focus in on the t-test, the t-critical, and the p-value. Some of them only have, maybe one of those or 2 of those, okay? So you should be able to make a decision by the outputs of that. Okay, so let's go on to the next one. Oh wow, how did the board get so clean? So now we're moving on to the next one. Example 5, is the mean body temperature really 98.6 degrees Fahrenheit? Okay, so data set 2 from body temperatures in Appendix B includes measured body temperatures with these statistics for 12 a.m. on day 2. N equals 106, X bar equals 98.2 degrees Fahrenheit, standard deviation is 0.62 degrees Fahrenheit. Use alpha 0.05 significance level to test the common belief that the population mean is 98.6. Right, so we'll start off with what I like to say is step 0. When do they give us? They give us the mean is 98.6 degrees Fahrenheit. They also give us our sample size is 106. They also give us our standard deviation is 0.62. They give us an alpha 0.05. Okay. And our X bar, actually, let me be careful. I think our X bar is 98.2. Our mu, our population, our previously known population is 98.6. That's what's commonly known as the standard or the mean body temperature. Okay, so I think I have what we need. So now move on to step 1 to step 3, which is set up the hypotheses. The no in this case is, don't think too hard, it's right there. Okay, whatever you put for the mean, that's the null hypothesis. The alternative would be, well, in this question it says use alpha equals to 0.05 significance to test the common belief that the population mean is 98.6. So we're testing this. In other words, the no would be that it's not 98.6. So this is a what? Left-tailed, right-tailed, or two-tailed test. That's right, it's a two-tailed test. So we're going to go ahead and calculate steps 4 through 6, which step 4 would be determine the alpha, 0.05. Step 5, determine the test statistic, which the appropriate test statistic here is, because we have X bar and S, we're going to use t-test. Before we had p hat and p, so we would use z-test for the proportions. So now we're going to use the same formula we just did earlier, which is n over the square root of n. Calculate by substitution first, 98.2 minus 98.6 over s, which is 0.62, divided by the square root of n, which is 106. Input that into a calculator and you should get it. Okay, so I get negative 6.642 as my t-test. Okay, and here they didn't really specify what to do, so we'll just have to decide if we want to do p-value method or not. So let's go ahead and do it both ways. I'm going to do a p-value method. So here's the picture for p-value. 6.62. I always think 3 standard deviation contains most of it. So 6.62, well actually it's negative, right? But I'm going to leave that one for what I'm going to say in a little bit. Negative 6.642. Now keep in mind that this is a two-tailed test. So even though we have a t-test, the p-value is the area beyond the t-test, right? But, let me change the color. You have to consider that it's two tails, so you need to do the other side as well, okay, to find the correct p-value. So whatever you get from this side, you will have to double it, okay? So I'm going to do normal CDF, not normal CDF, TCDF, lower negative infinity to upper is negative 6.642, degrees of freedom 105. You can put that into your calculator, second bars, TCDF, all the way to negative 6.642, degrees of freedom 105, because the sample size is 106, and I get a p-value of 0.0000000703. Okay, very small p-value. Okay, so right there should tell us a little bit. In fact, I mean, we pretty much have it. I'm just checking my p-value. Oh, actually, I need to double that, right? Yeah, that's right. So I need to double that times 2, I should put. Times 2, not going to matter. But now it'll be 0.00040, 8 zeros. 8 zeros and 1406. Okay. Doesn't matter. Sometimes it will matter. In this case, it won't. The p-value is 0.000001406, right? Is that less than alpha? Yes. So our conclusion, since p-value is less than alpha, we reject H naught that, no. Okay, I had to think a little bit. Since p-value is less than alpha, we reject H naught that the mean body temperature is 98.6. Now, you might be thinking, well, hold on a second, huh? This biostatistics professor doesn't know what he's talking about. Consider we didn't write what the mean is. If we look carefully back at the problem, we should have wrote it. Where mu is the mean body temperature at, I want to say 12 noon or 12 a.m. Okay, well now maybe I'll believe this. Okay, this is the mean body temperature, maybe overall, at a random time of day, or at least previously known, but what about at 12 a.m.? Well, maybe people have different body temperatures at different times, so that's what this is testing. Which, according to this study, we found that we can reject that the mean body temperature at 12 a.m. is 98.6. Therefore, there is evidence to suggest H1, the alternative hypothesis that the mean body temperature at 12 a.m. is not 98.6. And we've finished. Okay, we've made our conclusion. Now doing it the other way, real quick, go back to step 7. Instead of calculating a p-value, we'll calculate the critical value. So if I calculate the critical value, our alpha is 0.05, it's a two-tailed test. So I have to use alpha over 2, which is 0.025. Alpha over 2, 0.025. Use inverse t. We want to find this t critical. So we'd have to do inverse t of area 0.025. Degrees of freedom 105. Okay, so do that real quick on your calculator. If I can find it, there it is. Okay, so second var's inverse t 0.025, degrees of freedom 105, paste, and I get t critical negative 1.98. Okay. By symmetry, this will be positive 1.98. Place your t test in here, and we'll see that it falls. If this is negative 1.98, t test would be well outside, negative 6.642. That's well outside, so it's in the critical region. So our conclusion would be similar, or basically, it would say since t test falls in the critical region, we reject H naught. Okay, and then the alternative statement is the same. So that concludes example 5 using the hypothesis testing. Okay, the only other thing we might do if we wanted to, although it doesn't ask, you can do the confidence interval argument too. Yeah, so you can do that as well, but it's going to be x bar minus t alpha over 2 times s over the square root of n less than the mu less than x bar plus t alpha over 2 times s over the square root of n. Okay. If you do this, you'll end up with your interval, which here you end up with 98.2 minus t alpha over 2 is going to happen to be the same thing as this because that's negative 1.98. S is 0.62 divided by the square root of 106 less than mu less than the same thing except plus over here. 0.2 plus 1.98 over 0.62 or times 0.62 over the square root of 106. Do that calculation. You should get 98.08 to 98.32. Okay, and that's your confidence interval, which you'll note that the null hypothesis is not contained in there, so that's evidence to reject the null hypothesis. This is a 90% confidence interval. I'm not going to write the statements out, but that's all I'll say. The null is not contained in there, therefore it's evidence to reject the null hypothesis. Okay, so good. Now there are some follow-up examples. Some of these are just more of outputs. Yeah, like 30. Slide 30 is just body temperature. Your p-value is 0.004, so it's less than alpha, so you're going to reject you have to set up the null, set up the alternative. But since p-value is 0.0004, it's going to be less than alpha, so you reject the null. On that same slide about platelets, your alpha your p-value is 0.188, which at an alpha of 0.05 would be greater than, so you failed to reject the null hypothesis. So that's all I'll say about that. We may do, yeah, I think I'll only do one more, okay? The garlic one. So sometimes I put more than necessary. We've pretty much gone through the lesson. But let's do this one here. Okay, so this one says, in a test of effectiveness of garlic for lowering cholesterol, 49 subjects were treated with raw garlic. Cholesterol levels were measured before and after the treatment. The changes before, minus, and after in their levels of low-density lipoprotein, LDL cholesterol, have a mean of 0.4 and a standard deviation of 21. So I'm going to start writing some of this down. X bar is 0.4, and S from this sample is 21 in 49 subjects. N equals 49 subjects. Okay, so use alpha 0.05 to test the claim with garlic treatment. The mean change in LDL cholesterol is greater than 0. Okay, so mean is 0, alpha 0.05 again is pretty common, but it can be other things. Okay, so let's start. So that's step 0. Step 1 through 3, state our hypothesis. So the mean is equal to 0. Again, don't think too hard. Your alternative says that the mean change is greater than 0, so the mean change, and then define the mean where changes in their levels of load. Changes in low density in LDL cholesterol, where mu is the mean change of LDL cholesterol. Okay, so that's done. Step 4 through 6, alpha 0.05. The test we're using is the same test we've been using in this video, over S divided by the square root of N. Go ahead and plug that in. You get 0.4 minus mu, which is 0, over S, which is 2.1, I think, not the standard deviation of 21. Oh, it is 21. Okay, 21 divided by the square root of 49. We'll calculate this, and we'll get t-test. Okay, this is 0.1333, and part of step 6 or step 7 would now be the p-value. Calculate the p-value, which this is a right tail test. So 0.133, if that's 0, 0.133 would be here. And then I'd want to use TCDF with the lower at 0.133. Okay, and I want the area to the right, so the upper would be infinity with the degrees of freedom of 20. No, not 20, 48. So I'm going to input that, do TCDF, and that'll give us our p-value. Okay, second bar, TCDF, 0.133, upper infinity. Degrees of freedom, 48. 0.447 is our p-value. Which tells us, since p-value is greater than alpha at 0.447, alpha is 0.05, we fail to reject H naught that the mean difference in mean change of LDL cholesterol is 0. There is no evidence to suggest H1 is true. That mean change of LDL is greater than 0 with garlic. Right? I should have put that there. I'm just going to put it at that with garlic. That's where you're testing, right? You know, a lot of ideas. Somebody can say, oh, I wonder if garlic changes LDL cholesterol. That's how these hypotheses come about. Okay, so in a nutshell, on this one I just did the p-value. You could also use the critical value method, but that's it for today. Again, we usually don't. I put some extra ones on there, but that's just if we have time. But this would pretty much cover all of it. Okay, the other ones are pretty much the same. With that, you should be able to finish your homework. So make sure you do that, and I will see you next time.